Today, we are very happy to invite Dr. Sam Liu, who is an assistant professor at Acadia University, to as our first guest speaker. So Dr. Liu got his PhD from Stevens Institute of Technology, where he focused on sport biomechanics, and his research studies how human bodies move in sports such as like baseball pitching or basketball jumping, and how strength and coordination affect the performance. And I saw some of you interested in physical therapy, so it is a good chance to learning from Dr. Liu. Please join me to welcome Dr. Liu give us the speaker today. So Sam, I will turn the laptop this way so you can see the student. Can you see them?
Yes. All right. So good afternoon, everyone. So yeah, welcome to my talk. Today, I'll be giving a broad overview of introduction to sports biomechanics, the way I've been trained to view it, and also the way that I've used it in industry, as I'll go into some experiences a bit later. So the outline for today, I'm going to first introduce myself more personally, as well as the kind of research I've been doing, and then cover some more fundamental aspects of sports biomechanics, some of the tools that we use to quantify movements and performance in sports biomechanics, and lastly, some more higher level applications of sports biomechanics. So to start, usually I do this interactive exercise to have people guess which continent I was born in. But I was actually born in New Zealand. I'm sure that's probably on nobody's mind at the beginning. Then I moved back to China when I was 2. I did my middle school when I was in Australia. And then I went to the UK, where I did my undergraduate and master's degree at Oxford in engineering science. I also played a little basketball there. So that's the central through line of my life, really, is playing sports. So for my master's degree, I did a biomechanical modeling of the forefoot motions, looking at how people, like both healthy and clinical and older adults and young kids, how their foot moves in straight line walking and turning. But being an athlete, I wanted to look at a lot more interesting and dynamic movements for my PhD. So that's why I went to Stevens Institute of Technology in New Jersey, right next to New York City. And I wanted to study both baseball pitching and basketball jumping and dunking. And throughout my years, I did some internships, one with the Phillies, working in their Clearwater minor league team. And then last year, really for the past half a year, I worked with the Marlins in their major league location, again, both working in the biomechanics space. So here's my general research interest and themes. So number one, I like to apply a very much fundamental mechanics-based approach to understand how momentum of the body are being controlled in a variety of tasks. So 2 of the major movements in my dissertation involves a running jump and dunk of 2 feet. So I'm looking at how forces that we generate as we interact with the ground relates to how high we jump and how our body is controlled. I also research baseball pitching biomechanics using both professional and high school athletes data, looking at how rotations are being generated. And lastly, I also collaborated with additional other researchers in our lab in clinical walking and gait. And this diagram here at the bottom is from a study looking at how older adults navigate 90-degree turns to the left. As you can imagine, most of us go through our day-to-day life without thinking too much about the challenges or mechanical requirements of turning. But if you have impaired balance, such as being an older adult or have some other sort of diseases, then this is actually a very complex and challenging task that's also risky in terms of falling on your side and resulting in hip fractures. The other one of my main research interests is to understand different factors, biomechanical and physiological, underpinning movement control and performance. And the general idea is that we work within the constraints of our mobility, of our strength at different joints. And that's what really organizes the way we move. So those factors are key to not only what we can intervene and train, but also better understand, why people are moving a certain way. And lastly, this newer research line comes from developing and characterizing plyometric progressions. And the idea is to use it to first biomechanically quantify and validate progressions of plyometric exercises. And the idea is to help people retain their ability to move at speed and to handle impact even as they age. So this is going beyond just having athletes trying to jump higher to dunk or to improve their sprint performance. It's about making sure the older adults have the physical capability to pick up their feet and put it down quickly when it's needed to correct their balance and not to fall. So these four on the top left corner, that's what my dissertation research was about. So now let's start with a higher level introduction of what biomechanics is, and then into what sports biomechanics is. So by definition, it is the application of mechanical principles to human movement. So that involves aspects of engineering, physics, anatomy, and physiology. That's sort of go through all of biomechanics field in general. And specific to sports biomechanics, we also want to add in layers for motor control and sports know-how specific to the movements to obviously help improve performance and help navigate pain and injuries and hopefully help reduce it. And these aims have clear competitive benefits, but there are additional social, societal benefits to better understanding sports as well, because A, we know a healthy and active lifestyle is a key to long-term, happy living. So sports play a major role in, making sure that people better understanding sports play a major role into how people can age gracefully and have a higher quality of life. So now let's talk about some big concepts behind biomechanics. And the idea is to hopefully tie in with some of the mechanical concepts or sort of laws of motion stuff that you guys already learned in your mechanical engineering class or in high school physics. And then to fold it into the analysis framework that we typically use to understand movement control. So we just briefly, highlight Newton's laws of motion and then contextualize it in biomechanics. So first, Newton's first law of inertia, everybody can probably recall what it is. So the body's momentum will remain constant unless acted upon by a net external force. So here you have the bottom left corner, an example of a static standing situation where the downward body weight due to gravity is exactly equal to the upward reaction forces from the ground, resulting in a net force of 0 and no changes in the body's momentum. And the reason the body's momentum is being used instead of motion or something is because this also applies if we assume this also applies when we have constant motion, right? If the velocity of the body is constant, then again, you have net force of 0 that's completely balanced. And the only way to change your body's momentum for this example in the, given the recent Winter Olympic Games, the only way to change your body's momentum is to either generate propulsive forces against the ice or braking forces against the ice, right? To change your body's momentum in that horizontal direction. Right. So here's an example of what we call in sports a counter movement jump. So here we notice that when the athlete is staying stationarily still on the force plates, his momentum is not changing. And the only time point that the body is starting to drop down is because there is an unbalanced external force. By bending the knees and letting us drop, the downward force from your gravity or the weight exceeds that of your supportive force. And that's what this graph on the right measures. So we see that, here's how much force there is for the body weight. Because our reaction force is lower than body weight, we're going downwards. Once the reaction force exceeds body weight, that's when we are accelerating upwards. So this is really a manifestation of Newton's first law in this jumping movement. So what this means is that changes in the body's motion can only occur when there's unbalanced external force. Newton's second law is probably one of the most popular. The simplified version is force equals mass times acceleration. So we all generally know if we apply the same amount of force, it's going to be way harder to accelerate a heavier or more massive object than it is to a lighter or less massive object. And this generally manifests in human movement in the way people move. So for each of these three athletes, these are all NBA players at a combine test. And we're basically trying to figure out their movement strategies they use to jump as high as possible, again, from the counter movement jump or stationary up and down jump. Each of these athletes, they have very different movement strategies, and these movement strategies reflect the force generation requirements of their body. If you are heavier or more massive, you're going to move in a way that makes sure you maximize force generation and therefore your acceleration for your own body. And this is a hugely important part in analyzing movements because of how different humans have different body shapes, body types, and they're going to be moving differently. And to dive a little deeper, because I'm aware that you guys are mechanical engineering department. So if you integrate both sides of the F equals ma equation, you get the other format of Newton's second law, which is the impulse and momentum relationship. So here we have the force applied over duration is equal to the body's change in linear momentum. Similarly, we can change the body's angular momentum in the same way. So I'll go through some examples. In the linear momentum change example, so here's a figure of a running jump without a basketball for my dissertation paper. We have horizontal momentum forward coming in at the end of the run-up. And then as each foot contacts the ground, they generate forces against the ground that propels our body upward and slow down the body's linear momentum in the forward direction. And that's what allows us to complete the task. So this sort of shows that we can explain how the body's momentum changes by studying forces against the ground. For angular momentum change, this is one paper done by a couple of authors with some of the coolest last names, Small and Neptune, very fitting for gymnastics. And they're looking at how the body's angular momentum is being controlled in a balanced beam routine. And the idea is, in order to change the body's angular momentum through space, to do this backward somersault, you needed to generate moments about the body's center of mass to facilitate that rotation. And I'll go into that in a bit more detail later on. So now, just to sort of rehash the impulse and momentum relationship. So here we have the initial linear momentum of the body that's going forward and downward from the end of the running approach. And our final linear momentum at takeoff as we're going towards the hoop. What we can do is we can measure how each leg interacts with the ground with force plates, integrate those over time to give us our impulse. And then we have our upward impulse as well as our downward impulse due to gravity. We sum each of these ones up, and that causally explains how we get from here to here. And that's sort of the value of looking at movements through the lens of the impulse-momentum relationship. And now just to briefly touch on the most unique law, the Newton's laws of motion, as that of action-reaction. So we generally know whenever we apply force against something, there's an equal opposite reaction force. In the case of biomechanics, that typically is happening between the interface of the body and that of the ground. And we call the reaction force in biomechanics the ground reaction force. So how many basketball fans do we have in the room? Could you guys put your hand up if you're one? Okay, so just one I can see. But anyway, this has been a really big point of discussion in the biomechanics and the basketball world. So if you watch the NBA finals in this past season, you probably know generally what's going to happen. So this is a step backwards where we have an Achilles rupture. And we see this sort of stepping in a lot of more recent Achilles tendon ruptures over the past few years. So I made a little compilation just to demonstrate one point. A lot of times when people look at these movements in isolation, they're all blaming the backward stepping motion. This is probably the most clear. They're all blaming the right foot stepping backward as the culprit. But if we consider movement from the lens of Newton's laws, this foot placement down really is the best way to apply forces backwards against the ground to accelerate our body forward. So all of these movement things that we see, or all of these movement techniques, they are sort of framed and contextualized by the priority to apply force against the ground. And this is sort of the power of, having a more complete approach when it comes to looking at movements and biomechanics. And now we'll talk a bit about forces and rotations. So here we have a child walking, and these arrows represent the reaction forces from the ground. So at heel strike, the force is going to be applied at the heel, pointing very close to the body center mass of the child. At toe off, we have the forces at the toe. So to maintain balance, we generally want forces to point very close to the body center of mass, and that minimizes a moment generated by the force. But in other cases, when you have forces pointing away from the body center of mass, it facilitates rotation generation, whether that rotation is bad in the case of you getting tripped, and the force is pointing way away from the center of mass, and therefore creating a rotation in this direction. Or when rotation is ideal, when you want to generate rotations during this gymnastics exercise, where, again, in this case, it's your hands applying the external force, but still, you're trying to create rotation in this direction. And this is something I sort of analyzed in my first biomechanics paper in my PhD, where I found that during pitching, it is this little force that's pointed away from the body center of mass that's responsible for a lot of rotation generation during the baseball pitching. So that's why looking at forces, regardless if they're big or small, it's really what's also important is their direction from the body center of mass. All right, so now I'll go through the analysis framework in case you are interested into taking a little bit further into either physical therapy, biomechanical analysis, working with major league sports teams in sports science. So the most important thing when it comes to preparing for athletes is to understand the demands of sport. What kind of movements are used in the sport? Why are they used in the sport? Should you intervene when people are moving a certain way? And how should you be intervening? So this is the framework that you should really be considering, and starting at the top bucket of the task objectives, which is the overall goal of the movement. And these are generally very well defined for the sport. And I'll go through an example in the next slide. Then you put on your mechanical engineer hat and look at the mechanical objectives of the movements. So that's basically from an impulse and momentum perspective, what needs to happen in order for you to successfully complete the movement. What strategies are they using to satisfy those objectives? And then their individual movement technique. So that includes their individual kinematics or their positions, and kinetics and the forces they generate. And a lot of the time, if you think back to any coaches you had when you were growing up playing a sport, they all jump straight to this. Everybody focuses straight to technique, when in fact it's affected and governed by all of these priorities and all of these buckets above. And lastly, you need to consider, okay, how are your individual abilities shaping each of these above things or limiting it? And that includes something like mobility, your strength, and your coordination or training and movement history. So the most important thing to take away is that training and rehabilitation can happen and affect all of these levels, and they can affect these levels differently. So this is very important for any practitioners to keep in mind. So let's take an example of baseball pitching. So in the case of the baseball, there's a professional pitcher in our research study. The idea is to optimize the ball momentum and velocity as well as movements. And to do that, they need to generate and transfer momentum through the body by interacting with the ground. So you see the forces. It starts with slightly pointing forward, and then the back leg does a lot of the propulsion and rotation generation, and the front leg does the braking and more rotation generation. So what strategies are they using to satisfy these objectives? Well, they have to generate impulses by each leg to regulate the body's momentum. And then they use specific limb and joint positions to generate forces against these throwing arm body segments and the ball, and to transfer the momentum into the ball in order to achieve the task objective. And lastly, all athletes are limited by how mobile their shoulders are, how strong their upper and lower limbs are, as well as their training history, their technique, and their coordination. So now I'll talk a bit about different biomechanics measurement tools to look at the motion, the force, muscle activities, and any sort of computational simulations. So we start by talking about measurements of motion, or kinematics, as you'll come to learn soon. So the most common tool and the most historical tool are these motion capture cameras. They're usually set up at a rig that's sort of around the capture volume of the space you're looking at, and they are all irradiating infrared light, looking at these different reflective markers that we attach to bony parts of the athlete's or the actress's body. And a lot of times these setups are being used in both entertainment. So that's sort of what you remember from films like Avatar or the Marvel movies where they're trying to do motion capture, as well as biomechanical research. So a lot of these companies that are in these fields, they're always hiring for engineers and biomechanists, and they serve both entertainment, research, clinical, hospital, sports, etc. So you have these setups that we're trying to capture movements of the body in space, and this is what you can see at the background, where they can only capture the locations of these markers or reflective dots. And then it is up to either softwares that you have to pay money to use, or biomechanists like me to reconstruct the biomechanical model of the body from these marker data. So that's one major way that motion are being measured. And it also goes beyond biomechanics, as I know back at Stevens, one of the labs that studies drone movements and programming, they also put reflective markers and motion capture cameras to look at how drones fly in different formations. So that's pretty cool. Another thing that we have that doesn't rely on expensive camera setups are accelerometers. So again, if you're in biomechanics or electrical engineering, you might be familiar with this. These are devices, again, that we apply to the body, attach to the body, and it captures the linear acceleration of these different body segments, as well as angular velocity, and sometimes GPS signals. If you want to capture movements in indoor, though, the GPS signals usually are pretty bad. So we only usually use the linear acceleration and angular velocities. Recently, there's also been a lot more markerless motion capture. So that relies on very high fidelity slow motion video cameras, but you don't have to put any markers on. Because one reality of like trying to record biomechanics is usually it takes like an hour to put these on, and these can fall off. Like when I did my dunking biomechanics dissertation project, I started off by putting these markers on individually, and then warmed up for my jump. In my first dunk, 5 markers flew off, and I have no idea which ones they're from. So if I had the sort of markerless motion capture set up, you're going to have a participant come in, they do your warm up, you do your briefing, and they can just go. It makes the data collection process a lot more time efficient and convenient and accessible. And these technologies has also been starting to be used in baseball, professional baseball stadiums, where if you go to the next time you go to like a major league or even sometimes minor league baseball stadiums, you're going to have motion capture cameras all around the stadium from Hawkeye, and they're trying to capture the motions of the athletes pitching in game. And I'll touch a little bit about that later on in my the applications part. So now let's talk a bit about measurements of forces. So I am a big fan of measuring how you interact with the environment, and force plates is one of the best tools to do that. So we know, and as an athlete sort of pushes into the ground, there is the equal opposite ground reaction force, and that's what these measure. So this setup is actually from a very cool lab in Japan where they have a 40-meter track or more lined up with force plates. I think it's like 100 meters. So imagine every single step you take when you're sprinting is being captured by these force plates. And you can see how you transition from the acceleration phase all the way to upright sprinting and how those forces change. So the way forces work, these force plates work, is that they have, so if you look at this bottom left corner, they have these pressure sensing gauges, strain gauges, at each of the corners of the plate. So as an athlete pushes against the force plate at any of the locations, they are going to have different readings because of their different distances from where the force is being applied. So if you do a sum of forces and a sum of moments, you're able to get the 3D ground reaction force vector and additional vectors such as the TZ, the free moment, or the surface torque, and other stuff to basically summarize your interaction with the ground in totality. So, if you want to write your sum of moments, you want to write your mechanics equations, this is all you need, really. A lot of times in sports teams, so just to go backwards a little bit, these measures forces in all 3 directions. So that's what gives you the totality of forces. So you can look at braking, propulsive, you can look at vertical forces. a lot of times in professional sports teams, they only have force plates that measure forces in only a single direction, that is up or down. So if you consider, the degrees of freedom and how people move, this is great if your movement is primarily in the up or down direction, like a single leg or a double leg, stationary jump or a counter movement jump. But if you want to better understand how athletes control their body's momentum, this is wholly inadequate, right? And this is something that you, as a biomechanist, you have to sell and go to the coach or the strength coach or performance science department and be like, hey, this is great for studying this one specific movement, but we need to be careful in how we can how we can sort of take these findings and apply it to movements that are more dynamic and more contextual to the sport. And lastly, there are these pressure sensing insoles that you wear into the foot. So this allows you to get an even spread of whether you're putting more forces on the heels or the toes in a variety of movements. But again, this only measures forces in a normal or a planar direction. It's very difficult to measure shear forces or horizontal forces. And this is just a slightly different setup of a pressure mats. And these are being used quite a lot in different PT clinics to gauge, both how healthy and sort of, for example, patients with diabetes, how weight is being distributed as they stand and as they walk around. Then we have measurements of muscle activities. And the most prominent tool is EMG or electromyography. And this is from, if you guys go to the gym, you probably heard of Brett Contreras. So this is one of his glute muscle activation studies, where you have these sensors that captures the electrical signals being sent from your nervous system all the way to your muscle cells, and sort of converts them into these pulses of voltages. Some of these setups require wired, so the sensors are connected through wires to a sort of central unit, and then that communicates with the laptop. The other sensors, they can have onboard storage, so all you have to do is to stick it on the muscle groups, and then have the participants do their activities. So these signals, they usually come into these little pockets, and they're being, it's called rectified, but really they just apply absolute values to these signals. They filter it to get the general on and off signals, and then they sort of do a low pass filter to better understand, how and when the muscles are turning on and off. So this is a great way for people to get an idea of muscle coordination and activation. But one thing that's not ideal with these is it's very sensitive to noise from like even your soft tissues jiggling. So if you're doing a fast movement tasks, or you have very high level of activation, and you're going to be like slightly trembling, these are going to show up in your signals. But these are very difficult to play with. And also it relies you to very accurately place it on those muscle cells and spindles. But still, it's one of the great ways to directly look at what the heck the muscle is doing. Because otherwise, us biomechanists, we stop at the joint level, and we don't really know how exactly different muscles are coordinating to complete the tasks. So what are some other ways instead of these clunky EMGs? Well, more recently, not that recent, the past 20 years, there's this software called OpenSim. So people doing OpenSim research, they always hire a lot of people from machine learning, from computer science departments, where they're taking in biomechanical data, and then they're fitting it into a musculoskeletal model of the body, where they're trying to make sure that the model fits the best they can against the data. And then by doing a algorithm to try to either account for like muscle activities or maximize force application, they can then sort of model for what the expected muscle activation levels are to generate forces to pull against the bones around the joints in order to move your skeleton. So again, this is, if you're more interested in the modeling side, this is also very exciting and also, albeit very difficult venue of biomechanics beyond the simple equations that we went through earlier in the talk. All right, so now let's talk about the applications of the sports biomechanics research. And then that's pretty much the last part of the talk, so we can sort of open it up to more discussions and questions and answers later on. So one of the things that's been gaining a lot more popularity in the past couple years is the prevalence of gait or running gait testing. Like if you go to some more higher end shoe stores, they're gonna say, "Oh yeah, come do a running screening, and we're gonna find your best insoles, gonna view the best running shoes." And that's sort of one major use of biomechanics is to screen and test for a variety of different movements, and it's probably most common in running gait. Then this is a picture of from P3 Performance out in California, where they're running a variety of biomechanical testing for different NBA athletes pre-draft. And they look at a lot more things than what they do at the draft combine, such as lateral change of direction, biomechanical capture of running jumps. And again, this is the screen and test for their, not only their raw performance, but also how they're moving and where they are relative to the peers, as well as, they also group like movement strategies. So if you're quote unquote more muscular mover and take longer time to generate force against the ground, or if you're more quote unquote elastic, where you can bounce off the ground really quickly like a pinball and move very effectively. And lastly, is for injuries, screening, testing, predictions. It's very controversial topic, but there are general consensus into what specific positions places the most amount of load on specific tissues. So this is the case of injury screening against ACL injuries, where it is a combination of each of these three movements: ankle eversion of the rolling of the foot inward, knee abduction of the knee being moved more medially or towards the midline of the body, and femur adduction of the femur bone being brought closer again to the midline of the body. That the combination of the three places a high amount of stress on the ACL ligaments. Again, you can screen these and even quantify these with biomechanical measurements to understand, if someone's at risk of because of the way they're moving, or is something else happening in terms of, like, for example, a muscular weakness or poor control of their feet, for example. Then you have more ongoing monitoring and tracking. So this is what I mentioned before about the Hawkeye. So most people are probably familiar with Hawkeye cameras being used to capture, the lines and in and outs of tennis. But they've also began to use the same kind of high fidelity cameras to capture human movements during games and competitions. And what's the funny thing is, like, as I worked in baseball, professional baseball, Hawkeye is notoriously bad for their data quality issues, to the point that everyone sort of gives up on using Hawkeye and they reverted to a different model. So this one comes from the Kinatrax cameras, where it's capturing a lot more than a single pitcher on the mound in the center of the field. It's trying to capture how all basketball players are moving. I mean, even including the referee, right? If you want to study how there's one referee that tore his hemis when running back on the other side of the court. If you want to study that, right, you can capture the movements of the referees. But when you put all cameras around, then you can capture, how offensive players interact with defensive players, how their players play, perform different moves, how they go up for a dunk. And that's sort of what allows you to track and monitor movements in games and throughout the season. So as I was working in baseball, professional baseball, one thing they're really interested is how performance increases or decreases through the season and why that is. Is it because of, general fatigue, some changes in their structure, injuries, or just they change the way they think about the movements and that manifests in changes to their biomechanics? So all of these questions you can only answer if you're able to quantify movements to a higher enough accuracy and fidelity. And then, you have to dig through the data to analyze, why and how things are happening. And lastly, it's probably the thing that I was interested personally the most, and that's probably also why I came back to academia after a short stint with the Marlins, was I wanted to answer more fundamental questions regarding the mechanics of movements. So this is my baseball pitching research that looked at how forces we generate against the ground are being sort of distributed by each leg. So look at, here's what the back leg is doing in pitching. Here's what the front leg is doing in pitching, and how that manifests and changes to our body's momentum. And this is a follow-up paper of looking at, how's the momentum of the trunk being transferred to that of the throwing arm, and how that relates to ball speed, like, is more momentum in the throwing arm gonna be gonna result in more ball speed? There's this paper I touched on a little bit about before, where we're looking at the angular momentum of the gymnast during the somersault and how that helps, or sort of how it challenges the balance maintenance requirements of this movement. And back in 2008, there were a sort of seminal paper of applying momentum analysis in human walking. And these are done by two researchers at Harvard who was really interested in how momentum are being regulated and controlled in the task of moving. And we might think, oh, this is to apply to other adults or children, but no, this is to actually help them better build robots that actually walk. So if you look at the more recent popular videos from Boston Dynamics, a lot of these fundamental questions in biomechanics is also something they're trying to optimize and correct for. And instead of using machines, us biomechanists, we're just primarily looking at humans. And this is one other example. So next time, later on, you can try, and it's going to be quite obvious when you jump with an arm swing versus without. You're going to jump lower, but nobody really has a full explanation for why beyond of saying, oh, this arm swing makes me feel like I can put more force into the ground. So this is one paper that looks at the that looks at the energy analysis of these two movements. Like, for example, how much kinetic energy the shoulders generate versus how much potential energy you gain when you have arms overhead versus not. And again, these are sort of the more interesting papers that are interesting kinds of research that I'm personally more fascinated by. And lastly, if you wear a Nike shoe, you probably would like to hear that they do a lot of biomechanics research from their Nike Sports Science Research Lab out in Oregon, where again they do a lot of very similar things. They have markers and force sensors to look at how athletes perform different movements, and based on those mechanical requirements, they are then designing the equipment or shoe wear based on those sort of things. And obviously, there's other things like the Breaking 2 with the 2-hour marathon attempts, where they are playing with different shoe characteristics and capturing more exercise physiology. So that's looking at how much oxygen you're using per time when you have different footwear. And this is a company, BioCore, that's based in Virginia. And they actually do biomechanical analysis and modeling of helmets. So what they do is they use a lot of mechanical rigs, and they simulate collisions of the helmets onto the model of the dummy from different directions, and then compare, for this helmet, here's how good the force dampening is in each of the different directions. So again, if you're more interested in the design, manufacturing aspect, this is also, biomechanics is still a relevant piece for that. All right, so that's pretty much the talk that I have for today. So, now we can go into any sort of questions you may have. If you have any further questions or sort of idea suggestions, feel free to reach out to me with my Arcadia email.